Alright, hello everyone. So today we're going to be looking at complex numbers as vectors. So it's important to note that two-dimensional vectors, which we've covered in extension 1 vectors, and complex numbers, such as in our complex numbers topic that we're doing now, behave in the same way with addition and subtraction, but quite differently for multiplication. So we can divide complex numbers as well. We can raise them to powers and find their roots, which we can't do for two-dimensional vectors. In vectors, we are only interested in the direction of a two-dimensional vector as a concept, but in complex numbers, we're interested in the argument of a complex number, so we will use solve proofs involving rotation by certain arguments. So we can look at complex numbers as a vector. So for example, the vector OU represents a complex number U is A plus IB, which can be viewed as a vector starting at 0, which travels A units to the right and goes up by B units. Its tail is at 0 and its tip is at U. Now we have these two vectors here, OU and WV have the same magnitude and direction. That means they're equal vectors. So VW, the vector VW, is also A plus IB. And that follows everything we've learned in extension 1. Now we've talked about the Argand diagram before, and we're going to be using the Argand diagram and lots of different concepts involving that to solve these vector problems. So before we actually have a look at some examples of complex numbers as vectors, we're going to remind ourselves of a few laws. So we've got the parallelogram law of adding vectors. So we've seen that in extension 1. So we've got U plus V is that diagonal of the parallelogram. Subtracting vectors, remember the subtraction vector moves away from the vector we are subtracting. So in extension 1 I said the head of the second vector goes to the head of the first vector. Okay. Here we've got a polygon law, which is also useful for extension 1. So here, D plus A plus B plus C is just going to equal A plus B plus C plus D. And same idea on the other side. Remember, so we've got B plus D plus C plus A. Remember, vectors are just about displacement. So adding vectors from tail to head, we can just represent it as the addition. Okay. So we've got mark the points P and Q on the complex plane represents Z and W respectively. Mark the points R representing Z plus W and S representing Z minus W. Alright, so if we want to have a go at our parallelogram law, so we've got this here and this here. Now, Z plus W is going to equal that up there. That's by applying our parallelogram law. P will also go here, so Z plus W is here. Now, we also know that W is also this vector over here. Oh no, so yeah, W is also that vector over here. And we know that Z minus W is going to be this vector down here. So we're going Z minus W, the head of the second vector, over to the first. So Z minus W is that there. So Z minus W, if we will represent Z minus W as a point, it's going to be this vector over here. So that would be the position vector of Z minus W. The position vector of Z plus W is already there because it starts at the origin. So this would be point S, and this would be point R up here. And that's actually quite useful for extension 1 as well. Okay. Rotation and dilation. When a complex number is multiplied by another complex number, then starting with the original, we dilate or scale the modulus by the modulus of the second number. So we extend or contract the first complex number by the modulus of the second complex number. And we rotate the original vector by the argument of the second vector. So here if I've got U and I'm multiplying it by V, well here we can see U times V. Well, it's the magnitude of V times U, so it's going to be extended. But importantly for today's lesson, we can see that the arguments have been added together to get this overall argument there. So the work on complex numbers in vectors is far more likely to involve multiplication than division. However, division, remember, is the inverse operation of multiplication, so the effects occur in the opposite directions. So when we divide two vectors, instead of rotating anti-clockwise, which is the way we normally rotate arguments, if we divide vectors, we're going to rotate back the other way. Now we're also going to divide the modulus of the first complex number by the modulus of the second complex number. All right, dilation. When multiplying a complex number by another complex number, it rotates the original vector by the argument of the second vector anti-clockwise. Now that's because the argument of z1 times z2, remember, is argument of z1 plus the argument of z2. So as such, some important properties can be derived by this. Multiplying a complex number by I rotates the vector by the argument of I. Now we've seen quite a number of times that the argument of I going straight up is pi on 2. So as such, multiplying a vector by I rotates the vector by 90 degrees. Now in a similar fashion, multiplying it by minus I will rotate it by 90 degrees in the opposite direction. So multiplying it by a negative argument, or a negative complex number often, will rotate it in the other direction. So that it tells us that z and iz, the vector z and the vector iz, are at right angles to each other. Multiplication by 1 cis theta rotates the vector by theta but does not change its length. That's quite obvious because if you multiply a modulus by 1, it remains the same. And multiplication by k cis theta rotates the vector by theta and dilates it by a factor of k. Okay, got the complex number plane shows the complex numbers z and w. Mark possible positions for 2z. So z is here. So 2z, well we're not rotating at all. So 2z is just going to be double the length here. So that's a possible location for 2z. It means, the reason it says possible is because we don't have the exact length of z. So we're just kind of geometrically showing that it's double the size. A half w, well if that's w, a half w is simply just halfway. Now we don't, multiplying a complex number by a scalar does not affect its argument, and that's because the argument of any scalar is 0. Apart from if it's negative, the argument of a negative number is 180 degrees, so it actually rotates it by 180, or in other words, it sends it in the opposite direction. So following that, minus z is just going to be, oh, that's not the best there. Minus z is going to be here. And that's a half w. I wrote minus w, I meant to write minus z. Okay. Looking back at our extension 1 work, it is clear to see that to rotate a complex number without affecting its modulus will only occur if the modulus of the second vector is 1. In other words, we're multiplying it by a unit vector. So let's have a go at this. On the Argand diagram, we're going to plot the following. So we're going to draw a cute little Argand diagram. And now we're just going to locate z anywhere on this complex plane. So let's put it here. Z is here. Now iz is going to be the same complex number, but rotated by 90 degrees. So that's iz there. We might even put a right angle there. Z times cis pi on 3. Well, it's going to be the same complex number here, the same modulus, but it's going to be rotated by pi on 3. Z times 2 cis of 2 pi on 3. Well, we're going to be moving it over by 2 pi on 3. So 2 pi on 3 might be, well now 2 pi on 3, remember, is 2 on 3 is 120 degrees, so just a bit less than 180. So I reckon 2 pi on 3 might be like that, just a bit less than 180 degrees, but we're going to extend it and make it double the length because it's 2 times the modulus. So this is 2z of 2 pi on 2z, oh sorry, 2 times by, or z times by 2 cis of pi on 3, 2 pi on 3. Now we're going to have a look at z times cis of minus pi on 2. So minus pi on 2 is rotating it by 90 degrees in the other direction. So it's going to be right down here, and we're not changing its modulus at all. So that's 90 degrees there, and that's z times by cis of minus pi on 2. Now we might want to note up here that cis of minus pi on 2 is the complex number minus I, because it's minus pi on 2 is a negative angle going straight down. So cis of minus pi on 2 is minus I. So this has the same result as multiplying z by minus I. Something I want to note as well is when we rotate it, for example, by 2 pi on 3, it doesn't mean the argument of the complex number is 2 pi on 3. So part D, it doesn't go over here at 2 pi on 3 because we're not only rotating it by 2 pi on 3, but we're adding it to the original argument of the complex number. So if the original argument was 50 degrees, and 2 pi on 3 we know is 120 degrees, then the argument of the new complex number is going to be 50 plus 120, which is 170. So we're not just rotating it by, or moving it to 2 pi on 3, but we're also adding it to the original complex number, or the original argument of the complex number. Okay. The conjugate as a vector. The argument of the conjugate is a minus theta. Since the conjugate simply makes the imaginary component negative, hence we observe that the conjugate is just the vector, but it's reflected upon the x-axis. Okay. The complex plane shows the complex number z. Mark possible positions for iz, part 1, and b is iz bar. So iz is going to be that complex number rotated by 90 degrees. So up there. Now iz bar is just iz reflected upon the x-axis, so that's iz bar there. Okay. Question number 2 says, on the complex plane, P represents Z is equal to minus 3 plus 4i, and Q represents the complex number W. Find W so that the triangle OPQ is an isosceles right-angled triangle with the right angle at O. Okay. Might have a go at drawing this. Have a go at drawing a complex plane. And let's draw Z. So Z is minus 3 plus 4i. And that represents P. Now we're going to try and find W so that the triangle OPQ is isosceles with a right angle at O. So we've got a right angle at the origin. So that would be one triangle there. So that would be our complex number W. But we could also have it going this way. So we're going to have two possible answers, a right angle there. So that also could be W. Now we know to get a right angle, we're going to multiply a vector by I. So the W down the bottom in the third quadrant is simply going to be Z times by I, because it's just our complex number Z rotated by 90 degrees. And that's because it's an isosceles triangle, so the magnitude of that vector w is going to be the same magnitude of vector z. So iz is just I times by minus 3 plus 4i, which is minus 3i minus 4, which is minus 4 plus minus 4 minus 3i. Or we could have multiplied it by minus I. To go to the w in the first quadrant, we're rotating it by 90 degrees in the opposite direction, which we've already stated was the same as multiplying it by minus I. So minus iz is going to be minus I times by minus 3 plus 4i, which is 3i plus 4. So 4 plus 3i. Okay, part B says an isosceles right-angled triangle with the right angle at P. Let's have a go at drawing that again. So we've got vector P. And this time we've got a right angle at P. So it's an isosceles triangle, and it's either going to be that one there or that one over there. So this is W or that's W. And we're trying to find this vector here in red. What is that vector there? Well, I can tell already that this vector here that I'm going to I might highlight in green, it's still at right angles to P. So it's still vector z times by I. So this vector here is still iz, which we figured out was minus 3 minus 4, 3i. Minus 4 minus 3i. So to get from O over to W, we're going to go up along vector P and down along this vector here. So this is going to be the vector. So W is going to equal OP plus PW. Now OP is the complex number Z minus 3 plus 4i. And PW we just figured out was minus 4 minus 3i. So that would be minus 7 minus I. Okay, or we could have, if I get rid of some of this green here, add that back in. Or we could have the vector going along here and then up to there. So it's going to be W is equal to OP plus PW. Now OP is still minus 3 plus 4i, but PW is just our complex number P rotated by minus I or 90 degrees. So we're going in that opposite direction there. So it's just going to be plus our minus iz, which we already figured out was 4 plus 3i in the previous question. So we've got 1 plus 7i. Okay. Part C. We've got right angled at O with OQ twice the length of OP. So we draw in P. And we're told that it's right angled at O. So our two options are this one here or this one down here. So there's our two triangles there. But we're told that our vectors W, or the length of the other side of our triangle, is twice the length of OP. So in other words, to get the w in the third quadrant, well, we're going to go, okay, it's the complex number z times by, well, we're still rotating it by 90 degrees, so multiplied by I, but the modulus is doubled, so multiply by 2i. So we've got minus 3 plus 4i times by 2i, which is minus 6i minus 8, which is minus 8 minus 6i. Or we could have w is z times by, well, rotating it in the other direction is multiplying it by minus I or minus 90 degrees. But we're still doubling its modulus, so times that by 2. So z is minus 3 plus 4i, and we're timesing that by minus 2i. So here we've got positive 6i plus 8i, plus 8, pardon me. So it's 8 plus 6i. Okay, and those are our two answers there. Okay, last question for today. We've got the complex numbers 0, u, and v form the vertices of an equilateral triangle. Prove that, or show that u squared plus v squared is uv. Okay, let's have a go at plotting these, and we'll draw a random picture. So we've got an isosceles triangle, and we might call this V up here and this U here. Now we know that in an isosceles triangle, the interior angles are all pi on 3, or all 60 degrees. But from that, the argument of V is that, and the argument of U is that. So the argument of V minus the argument of U is equal to pi on 3. And because of that, if we get the complex number V, well, it's simply going to be U, which is this one here, times by cis of pi on 3, and that would get us up to there. So V is U times cos of pi on 3 plus I sine of pi on 3. So we're allowed to do that because cis of pi on 3 has a modulus of 1. So multiplying U by cis of pi on 3 is simply going to add only to its argument but not affect its modulus. Let's have a go at substituting that into our formula. So our formula, we're trying to prove that u squared plus v squared is equal to uv. Let's have a look at the left-hand side. The left-hand side is u squared plus, we figured out that v was u times by cos of pi on 3 plus I sine of pi on 3. And we're squaring that. Using De Moivre's theorem, we can say this is equal to u squared plus u squared cos of 2 pi on 3 plus I sine of 2 pi on 3. Now let's take out a factor of u squared from all of that. U squared, we've got 1 plus cos of 2 pi on 3 plus I sine of 2 pi on 3, which is u squared, 1 plus cos pi on 3 is minus a half, and I sine of 2 pi on 3 is root 3 on 2i. So it's u squared. Now 1 minus a half is a half, plus root 3 on 2i. Let's have a look at our right-hand side. Our right-hand side, we're trying to find uv. So let's multiply u and v. So uv, well, u is u, and v we figured out was u times by cos of pi on 3 plus I sine of pi on 3. Now u times u is u squared. Cos of pi on 3 is a half, and I sine of pi on 3 is root 3 on 2i. And that's the same as the right-hand side. So therefore, the left-hand side equals the right-hand side, and we're done. All right, thanks for listening.